Listen. Beneath the night, there is a story. Older than any map, louder than any temple bell. Tonight we step back, farther than memory, to the moment scientists have called, with wonder and with argument. The beginning. This is not the tale of one man, one flash, one answer. It is a chorus. Equations, observations, stubborn doubts. And the dates on which those voices first sang. 1922. A young Russian mathematician, Alexander Friedmann, took Einstein's new equations of general relativity and wrote something almost unimaginable. The math allowed a universe that could expand or contract. He published his solutions in 1922, not as prophecy, but as mathematics that said, the cosmos need not be frozen in time. 5 years later, in 1927, a Belgian priest and physicist named Georges Lemaître examined both theory and the sparse observations of distant nebulae. He proposed what he called a primeval atom, the radical idea that the universe had a hot, dense origin, concentrated in a single point from which space itself expanded. He published this hypothesis in 1927, and it took the world years to catch up with the imagination behind it. Then came the clear voice of observation. In 1929, Edwin Hubble combined distances and velocities of galaxies and showed a relationship. Farther galaxies seemed to recede faster. The sky was not static. Space itself was stretching. And with that stretch, the idea of a beginning became not just poetry, but measurable science. Science is not a single story. As the 1940s arrived, so did two vivid alternatives. On one side, the expanding universe line, building from Friedmann, Lemaître, and Hubble, suggested a hot, dense early state that cooled and spread. On the other, three men, Hermann Bondi, Thomas Gold, and Fred Hoyle, proposed the steady-state theory in 1948. The universe could expand, they said, but new matter would be continuously created, so the universe at large never changed. No beginning, no end, only perpetual now. Fred Hoyle, the most eloquent opponent of the early universe picture, gave a radio talk on March 28, 1949. From his mouth came a phrase intended as a rebuke, but the words took on a life of their own. He called it the Big Bang. Big Bang, a mockery turned brand. The phrase focused the argument and turned what had been a technical discussion into public drama. Did the universe have a single fiery origin, or was it eternal and unchanging in the grand scale? Into this debate stepped the theorists who tried to explain how the early fireball could have made the elements around us. George Gamow and his collaborators in the late 1940s pursued nucleosynthesis, the idea that the lightest elements were forged in the hot, early universe. Ralph Alpher and Robert Herman in 1948 took that idea further. They calculated that the leftover heat from such a hot origin should still be present today as a faint, uniform glow, a cosmic microwave background, at a few degrees above absolute zero. They published their calculation in 1948, predicting a relic radiation that would become the killer test between theories. Then, in 1964 to 1965, two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, measured a hiss, a hum, a persistent noise in their antenna. At first it was an embarrassment. Pigeon droppings, equipment failure, city interference. They cleaned the antenna. The noise remained. When they compared notes with cosmologists who had been expecting just such a relic, the implications exploded. That faint glow, measured in 1965, matched the predictions of a hot origin. The cosmic microwave background had been found. Penzias and Wilson's observation reshaped the debate. The steady-state theory lost its strongest empirical footing. The expanding universe, hot origin model rose. The Big Bang, once a derisive phrase, became the dominant scientific framework. But science didn't stop with victory laps. New questions arose like shadows. How exactly did the universe become so uniform? Where did its structure, galaxies, clusters, filaments come from? The 1960s and 1970s brought mathematical rigor to the earlier suspicions. Roger Penrose and Stephen Hawking proved theorems, now called singularity theorems, showing that under general relativity, Singularities were not an accident, but an expected consequence under broad conditions. Their theorems, developed in the 1960s and culminated in joint results by 1970, forced cosmologists to confront the fact that a boundary or a beginning-like condition was inherent to the classical theory. The Big Bang account worked, but small puzzles nagged. Why was the universe so uniform across vast distances? Why did space appear geometrically balanced? Why had magnetic monopoles not been found? In 1981, a new idea burst into the discourse: cosmic inflation. In January 1981, Alan Guth proposed that in the first fractions of a second the universe underwent an epoch of exponential expansion, a runaway stretch that smoothed, flattened, and diluted the cosmos. That brief ballooning, cosmic inflation, answered several nagging puzzles at once. Guth published his landmark paper in 1981, and it changed the story of the earliest moments forever. Inflation itself spawned a host of developments, and yet it pointed to an even deeper mystery. Whatever drove inflation, some exotic field, a vacuum energy, quantum phenomena at unheard-of densities, we had no direct observation of it. The early universe became a laboratory for the most speculative frontiers of physics: quantum fields, high-energy symmetries, and the interface between gravity and quantum theory. Scholars continued to wonder and argue. Some probed whether the Big Bang truly meant beginning, or whether quantum gravity could remove the singularity and replace it with a bounce, or a transition from an earlier phase. Others refined predictions so subtle they can only be tested with satellites and decades of signal processing. 1922, Alexander Friedmann published Expanding Universe Solutions to Einstein's Equations. 1927, Georges Lemaître proposed the primeval atom concept, a hot, dense origin for the universe. 1929, Edwin Hubble published the observational relation now called Hubble's law, the redshift distance relation showing cosmic expansion. 1948, Bondi, Gold, Hoyle presented the steady-state alternative, arguing for an eternal, self-renewing cosmos. 1948, Ralph Alpher and Robert Herman calculated that a thermal relic, a cosmic microwave background, should remain from a hot early phase. 1949, Fred Hoyle coined the phrase Big Bang during a BBC broadcast on March 28, 1949, as a pointed contrast to steady-state thinking. 1964 to 65, Arno Penzias and Robert Wilson measured the cosmic microwave background, the fossil glow that transformed debate into consensus. Let's be precise. The Big Bang model, as used by cosmologists today, is not a single sentence. It's a thick framework: general relativity describing large scales, a hot, dense early phase explaining the cosmic microwave background and primordial elements, inflation providing a mechanism for the observed uniformity and the origin of tiny fluctuations, and a wealth of observations, from galaxy surveys to microwave maps, that test the model. But precision brings new mysteries. We now speak of dark matter and dark energy, invisible substances or fields inferred from gravity and cosmic acceleration, which make up about 95% of the universe's contents. We still do not know the physical nature of these components. The Big Bang model explains the broad shape and development of the cosmos, but the identity of most of its substance remains cloaked. History is people. Friedmann's papers were almost ignored at first. Lemaître's ideas were slow to travel beyond language and war-scarred networks. Hoyle, brilliant contrarian, coined a term that stuck even as he fought the model it named. This story reminds us that science advances with stubbornness, with shyness, with loud disputes on radio waves and quiet calculations in offices. It advances when people look again at an antenna and find the hum of the universe. Which of these voices will the future agree with? Perhaps all of them, in ways none of us yet imagine. For tonight, remember the dates, the names Friedmann, Lemaître, Hubble, Alpher, Herman, Hoyle, Penzias, Wilson, Guth, and the sound they made when the sky first gave up its secret. The universe began as a question. Science turned it into a conversation. And that conversation continues.